In this video, we're going to take a look at acid-base stoichiometry with a special attention to titrations. Titration is probably one of the most important concepts that you'll see in grade 11, unit 4. It'll come back in grade 12, and you'll use titration as a common laboratory technique throughout careers in science. Even if you take biology, for example, it's a common technique used there as well. And we're seeing titrations in the context of acids and bases. And so by the end of this lesson, you'll understand what a titration is, what the purpose of it is, also what it looks like to carry it out. And then we'll also be able to do calculations that are titration related. So there is a great preview the material video here. It's the same one that we've been looking at for the acid-base introductions. So you can watch this one here, and now you'll be able to fully understand the part, or at least preview the material for titration specifically. In fact, what you see here, this setup, is a setup for a titration, which we'll be seeing in this video. So before we go into full titrations, I need you to get that we're looking at titrations from the perspective of acids and bases. So we're essentially doing neutralization reactions when we're doing a titration. Remember that there's two types of neutralization. You can have an acid base that gives you a water and a salt. So for example, here we have HCl, we have NaOH, and then we get H2O and NaCl. So here's our water, and here's our salt. So this is our acid and base, water and salt. Here we have H2CO3 with some potassium hydroxide, gives us some water, and then our salt, which is K2CO3 over here. So we have an acid base, acid over here, base over here, water, and a salt. So this is the general one that you're typically used to seeing, water and ionic salt. Now, another type of neutralization reaction that you might see is when you have an acid reacting with a base, but the base is a carbonate of some sort. So the base is, for example, sodium carbonate rather than sodium hydroxide. And in that case, what you get is you get your salt still, but you also get carbon dioxide, a gas, and water. Over here, same idea. So we have HBr and then KHCO3, a double displacement happens, and we get some CO2, some water, and then our salt over here. The CO2 and water came from the fact that when we made these two react, the H went with the HCO3 to make H2CO3, and it decomposed to CO2 and water. That was from our second unit when we saw the double displacements that have a decomposition that goes along with it. So typically that happens when you have an acid and some kind of carbonate compound. So as you can see, the neutralizations we've seen are acid-base, and in this case we see a base with an OH, gives us water and salt. You can see that the acids and bases are aqueous, the salt is typically aqueous, and the water is liquid because, well, you're not going to have a water solution of water. It's just going to be liquid. And in this case here, still a neutralization reaction. It becomes more towards the neutral when you put the acid and the base together. But instead, you're going to get three products. You'll get CO2 and water, and then your salt as well. And this comes from the decomposition of one of the products, which is the H2CO3. In all of these situations here with neutralization essentially means that you're coming closer to neutral. So your acid was a pH below 7, your base was a pH above 7, and when you mix them together, your water and salt solution is closer to 7. In some cases, it'll be exactly on 7. In other cases, it'll be exactly on 7. So for example, this one here is a case where it'll be exactly on 7. In other cases, you won't be exactly on 7. You'll be maybe a little bit above it or a little bit below it, but it depends on your acid and base that you're using. So you do need to understand neutralization when you mix acid and base together, and they can exist as either acid and hydroxide and then acid or carbonate, and either way you get something closer towards the neutral at the end. The reason we have to understand neutralization is because the titration is essentially that. It's a reaction between an acid and a base. A titration, the whole point of it is to be able to figure out the concentration of a solution using a solution that you know the concentration of. So for example, if I want to figure out the concentration of an acid here, I can use a concentration of a base. I can use a base of known concentration, make them react. Once the reaction happens, I can do some stoichiometry using my data and then figure out what the unknown concentration was. So that's what a titration is all about. It's using a known concentration, a solution of known concentration, to figure out the concentration of a solution, to figure out the concentration for a solution that you don't know yet. And so the two main tools that you're going to be using for a titration, this is a basic setup. You'll have a burette. A burette is a piece of glassware that basically lets you deliver very precise volumes of 2 decimal places, and you can deliver them drop by drop because these titration experiments are very, very need to be precise to get the proper concentration. So this is your burette over here. And the burette holds what's called the titrant. The titrant is the solution that you know the concentration for. So that's the one that you're going to be kind of using as your standard to figure out the unknown concentration of the solution here. So in the flask, that's where you would put what's called your analyte. The analyte is the solution of unknown concentration. And so you would see when the reaction happens, and you can use stoichiometry to say, well, if this concentration was this, and the reaction happened after this volume, then I know this concentration must be, Y, for example. So you're using stoichiometry to figure out the concentration of something you don't know through a titration. And the reason you do it with this technique, with this titration technique, is because you can do it drop by drop. You can be precise, and you can get a pretty good estimate of what this concentration is. So again, in the burette, you're going to put your known, which is your titrant. And then in the flask, you're going to put your unknown, which is your analyte. So let's take a look at how a titration works. So let's say that in this flask, I have an analyte and it's HCl. I don't know its concentration. It's my analyte. And in here, in the burette, I have a titrant. And I know its concentration. It's NaOH. Now, what I do is I basically add drops of NaOH into the HCl until the neutralization reaction is complete. So the point where the reaction is actually complete, or where the H plus completely neutralizes the OH minus, that's called the equivalence point. Okay. Now, acid-base reactions are kind of boring. They don't really have any color to them. So you have to add a color to them. You put an indicator. And when the indicator changes color, that basically says you're pretty close to your equivalence point. You're good enough to stop now. So equivalence point is when the H plus and the OH minus ions have actually all completely reacted with each other. That's when the neutralization is sort of done. And to indicate that, you need to put an indicator in there that will change color to kind of say, okay, equivalence points has been reached or will be reached soon, so you can slow down or you can stop. The point where the indicator changes color, that's called the end point. That's where you get an observable change that happens so you can see that you've reached your equivalence point. So let's look at this on the graph here. So I'm going to monitor the pH of the analyte as we start through the reaction. So initially, my HCl, before I add any base to it, pH of 2. I start to add base slowly, and notice the pH starts to go up a little bit. It's slow at first because there's a lot of HCl there and a little bit of base, but it starts to go up because some of the NaOH is reacting with the HCl, and we're taking away some H+. Okay, we're taking away some H+ in there. And so as a result of that, our pH is starting to go up. It's becoming less acidic. So I'm going to keep adding, and it slowly goes up until we get to this sort of part here where we've added so much of the titrant that now our pH will jump very quickly with the addition of any more drops. And so at this point, we're basically almost completely reacted our H plus and our OH minus. And once we get here, this value here, once we get over here, this is our equivalence point right here. So in this case, our equivalence point is at 7. My H plus is completely reacted with my OH minus, so I'm completely neutral here. And if I go beyond this, I've gone over the neutralization. Now I'm even more basic than before. So at this point, H plus and OH were matched. They cancel each other out. But if I add more base by accident, then I go over that equivalence point. The goal in your titration is to add enough base to kind of land somewhere near here. That's where you want to be. You may not exactly get to the equivalence point, but as long as you're in this sort of region here, that's pretty close, because notice there's not much of a change in volume here. You just want to be in this region, close to this, as close to this as possible in this steep region here. And so an indicator would basically change color maybe around here, sometimes within here, and that's when you know you would stop. If you go above, if you add more beyond this point, like I said, you keep going like this, you keep going, then you're going to overestimate your concentration of your analyte, and your estimation is not good anymore. So you need to become good at adding this sort of fast, but then slow once you get to a certain point, so that you just get a color change that just happens, and that's where roughly your equivalence point will be. So what I want you to get is that equivalence point is, chemically speaking, where the H plus and the OH minus have canceled each other out. The end point is where the color change of the indicator happens. They won't be exactly the same because you're not really going to have an indicator that'll change color at exactly the pH that you want it to change at. Okay, so it depends on your indicator, but typically it should fall within this area. Indicators will change color at a certain range of pH, and you should want it to fall within this little steep area here. So this, what we just studied here, is called the titration curve. It monitors the pH of the analyte as you add the titrant. So we have our acid here, pH of 2. We slowly start to add our titrant. So essentially our titrant's a base, and as a result of that, the pH is going to start to go up. So as we add the base dropwise, the H plus starts to get consumed by the OH minus, and so that's why our pH starts to go up a little bit. Now, step 2, this is the pH right before neutralization is about to happen. Like we're almost at the point where we've almost matched OH and H plus. So that right after this point, that's where we're going to jump up with any sudden change in volume, any sudden addition of NaOH. So basically, we just need to add a couple more drops, and once we do that, then we're at our equivalence point. That again is where all the H plus and the OH minus have essentially been have reacted, and then we need our end point afterwards. Our end point, that's going to be somewhere in here, in this steep portion here, and that's going to indicate or tell us that we've roughly reached our equivalence point, chemically speaking. And that's when we know to stop the titration, and we can use the data at that point to figure out the concentration of the unknown substance over here. Or not unknown substance, we know the substance, we just don't know its concentration. So this over here is the titration of a strong acid with a strong base. HCl is a strong acid, NaOH is a strong base. For the titration of a strong acid with a strong base, the equivalence point is going to be a pH of 7. That's going to be for any strong acid, strong base, equivalence point is a pH of 7. If you have weak acids, weak bases, then equivalence point may not be exactly 7. It might be a little bit more, a little bit less than 7, but closer to 7 than it was before. So that is basically what a titration looks like. This is our titration curve over here, and you should be able to explain what the titration curve is trying to show. So again, we're monitoring the pH of the analyte as we add titrant, which is NaOH. We add it dropwise with our burette here. So this here is our titration curve again. And here's our equivalence point. And over here, you can see a picture of an indicator that was used to tell us when we're getting close to our equivalence point. And so the idea is that we have our acid in here, and we're adding base, and it slowly starts to rise, slowly starts to rise, slowly starts to rise. And we're not really seeing much, but here's our equivalence point. And our indicator changes color roughly at this pH here, right about here. Okay, and we add a drop of it. We just add drops of it until our indicator starts to change color. When our indicator changes color, we want to make sure we stop. Otherwise, we go way over the equivalence point. Like once you're here, you've added way too much. You essentially want to be within this steep portion here. That's when your estimates, even though there's a little bit of error, are good because you only maybe added a drop or two more. Now, what I want you to notice is that this indicator, this is phenolphthalein, this here changes color over a range of pH. Notice it's kind of like it becomes like a light pink color to a darker pink color. So really, you want to aim, so this is your start, it's colorless, you add. You want to aim to get an endpoint that's a light pink color. If you go dark pink, that means you've kind of overshot, and it's dark pink even here. So we don't know are we dark pink because we're just right here, or are we dark pink because we're way up here? We don't know anymore. We've overshot it. We've gone too far. So we want to aim for an endpoint color that's sort of the lighter shade there. The lighter shade when it just changes color. A lighter color, lighter pink. And again, it's a little bit above our equivalence point, which is 7 in this case, but it's pretty close. It's within that steep range, so we didn't go above the volume too much that we had to add, and our data is going to be pretty close there. So this was an example of an indicator that was used to tell us when our endpoint would happen. If you forget to put your indicator, you're not going to see a color change, and you don't know when your endpoint happens. You can use digital pH monitors. That's a possibility as well. but we typically use indicators in our labs, in grade 11 labs and grade 12 labs. So this video here goes over titration curves in a bit more detail. I encourage you to watch it. It's a really good video that goes over this concept, and we'll give you different examples that you can try out as well within the video. So check it out. It's really great. Understand what the titration curve is. Understand that we want to aim for the lighter color change, because that means that we didn't overshoot. We didn't go over the equivalence point too much. We did a little bit, but the volume's not much. The pH and volume is not much of a difference here. It's when you go overshoot and you get a very dark color that we can't trust that data anymore. We have to retry it. So here's our titration in action. This is a little video that shows you what a titration looks like. I highly recommend that you watch this, because you will have to do titrations when you get back into the lab in school. I do want you to get some experience at least seeing what it looks like. I would typically recommend that you also draw a little doodle page or a little flow chart to describe the steps of a titration after watching this video, and label all the parts so you know what they are. So that way when you see the equipment, to go, oh yeah, that's that burette thing, that's that flask thing, that's the indicator. I know where to put everything, and then all you have to do is basically just put the practice that you did on paper into, well, actual physical practice. So here's how it works. You fill up your flask with the solution of unknown concentration. That's called your analyte. You add a few drops of indicator to your flask. And that won't really do much right away. It depends on what the indicator will vary depending on what your acid and base are, and where your equivalence point, where you think your equivalence point is going to be. You fill your burette with the titrant, which is the stuff of known concentration. So it might be a base that you know the concentration of. And what you do is you add the titrant drop by drop by drop to the flask until you get a color change that persists, that stays. Okay, it stays. But it has to be the light color change, the one that's like over here, the lighter color change here. So what we want to do is, when you're doing that, once you've reached your light color change, you can record data. Actually, you should record data earlier on. So typically what you do is you record the data, the initial data in the burette, the initial volume. So for example, let's say this is my trial here. Let's say I had a volume of 0.2 and my final reading is 15.3 once I got my color change. Well, the volume that I added is 15.1 because I went from 0.2 to 15.3. You should do 3 trials actually and take the average at the end of your volume of NaOH. Your whole goal is to find out how much NaOH of known concentration did I add, what volume, and I can use that to figure out the concentration of the solution's concentration I don't know. So this is a second trial here. Your initial burette reading was 15.3, and then we've got our light pink color at 30.5. That means we added 15.2. So it's 30.5 minus 15.3 gives you 15.2. Pretty close to our first trial. And then trial 3 over here, we started at 30.5. We went down to 45.5 here. So we can subtract them, and we added 15 milliliters of our base. And so in our final calculation to figure out the concentration of the acid, we would find the average volume and use that in our final calculation. So this table here is a general table you will see for titration. Generally, we put a table number, so table 1, titration of 20 mils of H2SO3 with 0.150 mole per liter NaOH. So the idea is that you know the volume of the acid you put in here, okay, but you don't know its concentration. And the NaOH is in the burette here. We know its concentration. So we say we titrated H2SO3 with this NaOH. We don't know the concentration of H2SO3, but once we figure out how much NaOH is required to neutralize it based on our color change, then we can do calculations to figure that out. So again, you typically need to do 3 trials of this to get 3 volumes. Notice we're all pretty close every single time. And you take the average at the end to get the average volume, and that's what you use for your calculation to find the final concentration. So I do encourage you to watch this video to see what exactly it looks like in action. These are the main steps over here. And they're pretty simplified, but it's basically all you have to do. Just make the reaction happen, see how long it takes to happen, what volume you need 3 times, and you're done. Generally, though, I usually say have a trial that you don't really count, like a practice trial, because if you have to add a drop by drop by drop by drop by drop, it'll take a long time. So I usually tell students to let the burette run at a faster flow rate, so it'll put more liquid in at a time. And then you just see roughly where the color change would start to happen. So you might not be very accurate the first time, So you don't really have to count that one, but you can see roughly the volume you had to add. And then that way you can go a bit faster at the beginning and then slow down where you think the color change will happen. So I usually do kind of a rough run at the beginning, but I don't really count just to see roughly where I'll be. So how do you read Burettes? Burettes are kind of interesting. They start off with 0 at the top, and then the numbers get bigger as you go down. So let's say at the top it was 0, I go 2, 3, and then in between 4, 5, 6, 7, 8, 22, 23. So it goes up as you go down, just because it tries to show you how much base or how much liquid you've put in. Okay, so it's trying to show you how much liquid you put in so you can do your subtraction. So essentially, let's say that my base level in my burette, so the burette is this thing over here. Let's go find a better picture. The burette is this over here. Let's say I start off at a level 2, 2.0 milliliters. Okay, so 2. Well, actually not 2. It's this is 2, 2.1, and then 2.20, about 2.20, maybe 2.21. So 2.20 over here. Okay, I let the base out until I see a change in color, and I notice that my final level where I end up at is about this is 22, 22.1, 0.2, 0.3, 0.4, about 0.5. Okay, so I was at, this is 22.50 over here, and this is 2.20. Okay, so you just do 22.5 minus 2.2, and that means I added 20.3 liters, or milliliters, sorry, 20.30 milliliters of my solution. That's what it took to neutralize or to get to an equivalence point, or end point, I should say, when the color change happened for my solution. So burette, you typically read them to 2 decimal places, And you just do your final area where you read from the meniscus minus your initial that you started off at, and that's the total volume that you used, and you would record those values in your titration table that you see here. So remember that when you are reading water levels or base levels or acid levels, you need to do that from eye level, and you have to read the meniscus, the bottom of the meniscus. So just remember to review that if you haven't already seen that. So again, it's a very picky experiment. It can often be very stressful because you never want to overshoot. You can be going and you want to get right to this color here, but all it takes is really an extra drop and you've overshot it, and that's not good. So it's really stressful. Students will often have one more drop to add, and it's kind of clinging there, and they don't want to turn this too much to add too much water, so to add too much of the solution. So they might just spray it with a little bit of water to get it off, or they might touch the little drop to the edge of the flask so it can slowly leak down. And it's very, very, very scary because you don't want to overshoot. Otherwise, your trial is not that great. So we often say that this is what happens when your resting heart rate. This is when you're exercising, and this is when you're doing a titration. You're just so stressed out about it. And you can also watch this video to see what happens when you overshoot. So again, this is just an idea of overshooting. And you can watch this video here again to see what happens when you overshoot there. So please make sure you watch that. But essentially what happens is you want to get as close to this as possible. And you need to use your indicator to tell you when you're close to that point. And you'll notice that this changes over a range of pH. So as long as your indicator is in this little area here, in this steep area, the steep area specifically, you're good. But you want your color change to happen kind of early on in that steep area. If it happens up here, I don't know if it happened because I added an extra drop or 2 drops, because it's still dark pink up here too. So it's just kind of a horrible trial. So you want to make sure you get the light area, because that means it just changed color roughly around here. And this is a good endpoint to be at. You're not too far above your equivalence point. And any error that's there is so small, you're going to be very close to your concentration anyways. So how do you know what indicator to choose? There's different indicators that exist out there, and it really depends on the acids and bases you're using. It depends on the type of titration you're doing. So, for example, if you have a strong acid, strong base titration, your equivalence point is going to be at about 7. Okay, it's going to be at 7 for strong acid, strong base. And so you want to choose an indicator that will change color within this steep portion here. You don't want to overlap with the curved portions. You want to be in the steep portions. So, for example, phenolphthalein, that will work here. Here we have, as we add in this case, we start off with our base in the flask and we're adding acid. And essentially we want to make sure that we get to just where we change colors to to colorless, from pink to colorless here. But basically phenolphthalein works well here because it's in the steep portion, pretty close to the equivalence point. This is another indicator here called methyl orange. Methyl orange will work well here because it's within the steep portion. So methyl orange can still work. Chances are phenolphthalein is a little bit better, but methyl orange is still pretty good in this scenario here because it's within the steep portion. You probably just want to use it once it turns this yellow color. You don't want to go too deep into the orange because that otherwise you'll overshoot and you'll go out of the steep portion. Now, you do have some titrations where you might have a strong acid with a weak base. Strong acid, weak base titrations, their equivalence point, you'll notice, is less than 7. And that's because you have a strong acid. So a strong acid will kind of carry that to being more acidic at the end. So even though it's a neutralization reaction, so to speak, the reaction with a strong acid, weak base will not be fully neutral. It'll be closer to the acidic range. So a little bit less than 7. Now you have to choose, if you had to choose an indicator for this titration, and I gave you two choices between phenolphthalein and methyl orange, which would you choose? So hopefully you chose methyl orange because it's within this steep portion here. Phenolphthalein is outside the steep portion. It's not close to that equivalence point. The equivalence point here we have 7, 6, 5, 4, about 4.8. So methyl orange changes color pretty close to this area here. And it's within the steep portion. So that makes this a pretty good indicator for this titration here. Now let's take a look at this titration over here. This is a strong base, weak acid titration. At equivalence point, the pH, because we have a strong base and a weak acid, the pH will be a little bit above 7. So we have 7, 8, 9, about, let's say 9.1 maybe. So that's our equivalence point there. So we have to choose which substance or which indicator would be the best indicator for this job. So try to think, would you want phenolphthalein or would you want methyl orange? So hopefully you chose phenolphthalein because notice that it changes color within the range, with basically right where that equivalence point is. And the methyl orange changes color, way after it. So you would have gone way beyond the equivalence point if you chose methyl orange. It's not within the steep portion of the curve, whereas the phenolphthalein is within the steep portion of the curve. So that's how you go about choosing indicators. We can try a few practice examples out here. So here we have a titration curve. We have, we're adding some NaOH to HCl. And so our pH is going up, and here's our equivalence point. And if you look, the equivalence point is at a pH of 7, which means this is a strong base and strong acid titration. So that answers the first question here. It's a strong acid, strong base titration because we are at a pH of 7 for our equivalence point. Now we have to determine the most appropriate indicator to use in this titration. So think about which indicator would be best to use, which indicator you could use in this titration here. So notice that you're adding base, so your pH is going up, and you want the color change to happen within this steep portion here. So in reality, both of these indicators fall within that steep portion. So you could use either one of these indicators. They would both be appropriate to use. If you're using methyl red, you might want to use it when it first turns red as opposed to go to yellow because you might overshoot. If you're using bromothymol blue, you might want to use it. You might want to wait till it turns yellow here, but you don't want to go to blue because then you'll overshoot. So you kind of want to stop the titration once your color change has just occurred. So for our methyl red, you want to go just red, the light red area there, because that means you just entered the steep portion. You don't want to go to yellow because that means we could have gone above it. Who knows? Because this is yellow actually beyond as well. And thymol blue, you got to be careful. So we want to basically go where it is turning just yellow, not in the blue, because then we've gone beyond that as well. So both of these will be appropriate because they're both in the steep portion and they change color sort of within that, very close to that equivalence point there. So let's try this one here. Similar question, but a little bit of a different titration that's happening. So is this a strong acid, strong acid, weak base, or strong base, weak acid titration? Justify your answer. You could read the title of the graph, but you won't always have the substances there. So notice that we do start off with something acidic in the flask. I know that because my pH is less than 7. It's pH of 3. And I start going up. I start adding some base, and then my pH increases. So notice that the equivalence point is above 7. Because the equivalence point is above 7, that makes this a strong base, weak acid titration. That strong base gives us an equivalence point that's above the 7 mark. And we have to pick which indicator is the better indicator for this reaction. So notice that methyl red is in the curved part. It's not in the steep portion here. So methyl red would probably not be very good. It'll change color far before the equivalence point is reached. And when you go to yellow, I mean, did we go above it? We don't know. It doesn't tell us much. We don't know where we are once we're yellow. But thymol blue, that's within the steep portion of the curve. It changes colors very close to the equivalence point of that's above 7 there, just a little bit above 7. So in the basic area, and notice that we'd probably want it to just turn yellow, because that's pretty close to the equivalent. If it goes blue, then chances are we overshot it. So let's take a look for right. That's right, strong base, weak acid, because we have a pH above 7 equivalence. And bromothymol blue or thymol blue would be the best or most appropriate indicator to use in this case, because it's close to the equivalent point, and it's within the steep portion of the curve. So here we have a few other ones that you can try out. So which indicators would you use for each titration? So you can pause this video and try it out, but just to give you some context, you have 2 titrations happening here. You have one with this little purple line and one with this red line. So let's take a look at the red line here. The red line, you'll notice that the equivalence point is pH of 7. So that means that we have a strong acid, strong base titration for the red line over here. And which indicator would we want to use? Well, in reality, we could probably use any indicator. The better ones would probably be phenolphthalein and the litmus pH range, litmus paper here, or the litmus if it's a liquid, you're using a liquid, for example. You might want to use any of these 2 here. You could maybe use the methyl orange. I'm just not sure how accurate this graph is, because it falls in that curved area there. It might be the less appropriate one to use, but maybe you could get away with using it. But the better ones would be the phenolphthalein and the litmus for the strong acid, strong base titration. And you could potentially get away with using the methyl orange here, because it is in this region here. It really shouldn't be overlapping with that curved part. So these would be the better ones here to use. Now, notice we do have a titration we have another titration here, and the equivalence point is at 8.72. And that means that we have a strong base being added to a weak acid, because our equivalence point is basic. So what indicators can we use? Well, I wouldn't use methyl orange for sure. It's not even the steep portion for this purple line here. I probably wouldn't use litmus either, because it overlaps with the steep portion, but it overlaps significantly with the curved portion here. So I wouldn't use litmus. The only one I would use for this titration for the purple line is the phenolphthalein, because that falls within that steep portion. It's really close to the equivalence point there of that there. So we said phenolphthalein can be used for both. Methyl orange could be used for the HCl titration, just barely, because it's still overlapping there, but it could barely be used. And then litmus could be used for the HCl titration as well. But phenolphthalein could definitely be used for both of the titrations. But it's the only one that can be used for this particular purple line titration there. So that was just an overall overview of titrations and reading titration curves. The last thing to mention, though, is notice most of the titration curves we saw, our flask had acid in it, and we knew that because the pH was lower than 7 at first, and then we added base from our burette. In these pictures, and at titration, you can switch things around. So in some titrations, you might have base in the flask, and acid in the burette. And that was the situation here, because in the flask, that's what you're monitoring to begin with. You want to see a change in pH as it happens. We have a pH above 7 to start off. So we had bases initially, and as we add the substance in the burette, the pH decreases. So it's still a titration curve. It still works out. It's just we flipped what we had in the flask and the burette in these situations here, but the concept still works the same way. So that was our overall concepts for titrations. You should know how to explain a titration curve, what happens at all these different points here. Now, I do want you to notice that here, these are the steps of what happens in a titration. Do understand that the equivalence point, again, is not the exact same as the end point. The end point is where the indicator changes color, and that won't be exactly at the equivalence point, but it'll be close enough to it as long as it's within this steeped portion of the graph.